right. Good. All right. So we're going to start today talking about work and energy and power and how all three of those go together. So to start off with, let's define work. Work occurs when an external, that's an external, not an internal system force, but an external force is applied over a distance. If I have a force applied over some distance, I get work. Work is a form of energy. It's going to affect the total energy of my system. We'll get to the work-energy theorem later. But work, oh man, I'm videotaping with my iPad, but that's what I carried around as an example for all of the last two classes. Okay, I have this physics textbook. Now I'm doing more work. Okay, so I have this physics textbook. I'm currently holding it, so I'm applying what force to this textbook? An applied force, right? I'm pushing which direction on it? Up. It would equate to the normal force that's acting on this textbook, right? So, if I currently hold it right here, I'm applying a force. Is it moving a distance? No. So therefore, without it moving a distance, how much work is being done by me? Zero. But, okay, I'm going to walk around. If I walk around, am I doing work to the textbook?
No. Yes.
Am I moving a distance?
Yes.
Yes, but is that distance in the same direction as the force I'm applying?
No.
No. And therefore, I am doing no work to the system. Hold on about 8 minutes, okay? Okay. Okay, you can turn it. Just in there. Yeah. Find a spot. Just set it down. This is perfect. Great. All right. So, I'm not currently doing any work to the book because my force is upwards and I was moving horizontally. So that does not work. If I apply the force upward and move it upward, now have I done work to it?
Yes.
Yeah, absolutely. I've done work to this object. Okay? Now, has its energy, the object by itself, it's not a part of a system, has the energy of this book changed? No, but I did work to it. Work is a change in energy. So why is the energy of this book not changed? I'm not part of the system, so I can do work to it. So it should have changed. What is the other force acting on the book? Gravity. Which direction is gravity pointing? Down. Which way did it move? Up. So did it do positive or negative work to the book? Negative. In the exact same amount that I did positive work to the book. So since the energy of the book didn't change, the book by itself, we're not counting anything else in its system, the book by itself, when I lifted it up, it did not experience a change in energy. Its kinetic energy is the same as before. That's because I did positive work to it, but gravity did negative work to it. All that work canceled out. Okay? So, as a reminder, what that means is that the equation for work is not simply force times distance. It's actually force with a dot product of distance. Force dot producted is a verb I like to coin. Force dot producted with distance. If you're terrified of a dot product, on the back of the pink sheet, the one that has mechanics on it, it tells you what a dot product is. A dot product is terrifying. It is FD cosine theta. Wow, okay, that was a lot of work. So as a reminder, distance only counts. Force only counts if they're going in the same direction. If the force and the distance are in complete opposite directions, 90 degrees apart, the angle between them would be 90, and so the cosine of 90 is 0. So this angle, as a reminder, is the angle between the distance that I travel and the force that is applied. So if I apply a force, let's say I pull a box at an angle. I do F pull, I pull a box at an angle, up at an angle like this. The work I do to the box would not be equal to my F pull times the distance I pull it. Why? Because there needs to be a cosine theta. Not all of my pulling force was in the direction that it went. If it goes this way, right, not all of that pulling force was in that direction. Some of it was up, and so some of my pulling force did not do work to this object, okay? So, when it comes to work, it is force times distance, but that force and distance have to be in the same direction. FYI, this cosine theta takes care of the positive and negative because, right, we said that gravity was doing negative work to that book. When it moved to distance that's positive, that's because if these are the force and the distance, what's the angle between them? 180. So the cosine of 180 is -1. So that cosine helps you out with whether work should be positive or negative as well. All right. Now, that is very AP Physics 1 of us. But what if the force isn't constant? This is predicated on the force being a constant amount, a specific number that stays the same the entire time. I'm pulling on the rope and I'm pulling on it with a constant amount of force the whole time. What if I don't? Well, I could rewrite this as work is the sum of the force I applied over a certain distance plus the sum of the force I applied over another distance plus the sum of the force I applied on another distance, so on and so forth, infinitesimally until I get an integral. Force, still a dot product with the change in r. Remember, r just represents a direction. It could be x, it could be y, it could be up at an angle, right? So f dot producted with, this should be distance. I don't know which direction the distance is in, but it's distance. So work, right, is the derivative of, the integral of force and distance, right? So let's see 2 ways this could look. First off, if I just give you an equation, I see an example, a variable force of e to the 2x is applied from x equals 0 to x equals 0.25 meters. What is the work done to the object? Whatever object this force is being applied to. I don't know what it is. A box, a book, something. So a variable force is applied from x equals 0 to x equals 0.25, and I want to know what is the work done. Okay? FYI, this doesn't involve any U substitution. This is a pretty simple integration. So at this point in AP Physics C, I should feel comfortable doing a simple integration of anything on this back sheet. So that includes the power function, that includes 1 over x, and that includes this e to the power function. So this would be work is the integral from 0 to 0.25. It gave me limits. Does everybody see that it gave me limits, right? The distance I covered was from 0 to 1/4 of a meter. Of e to the 2x dx. So, what is the integral of e to the 2x? E to the 2x over 2. Yep. So the a comes out 1 over a, and then the e to the power stays the exact same. I haven't used my limits yet, so that's what I'm going to do next. It would be 1/2 e to the 0.5 minus 0.5. E to the 0 power is how many? 1. 1 times 1/2 is 0.5. So if I solve this, this might be the first reasonable number I came up with all day. 0.5 e to the 0.5 minus 0.5. Well, it's more reasonable than the other ones. 0.32 joules. Haha. So not very much. 0.32 joules. So this is a type of question I could see. Okay? Another integral type question that I might run into would be this. If I give you a force over distance graph, and I tell you that it looks like that, how would I find the work done over this distance? Area under the curve, right? So integral could be two things. It could be I give you an equation and you take an integral. How cool. An integral could also be using area under the curve of a graph. Okay? Before we get to power, which is our second to last thing here, I just want to say this. They love doing this. Work is the integral of force and distance. So, what's the derivative of work with respect to distance? Force, yes. So just as a reminder, they don't do this very often, but it could work out that way. The derivative of work with respect to, I'll put R, but it could be X or Y. The derivative of work with respect to distance. We've really only done our derivatives with respect to time so far, so this is kind of a weird one. But just remember that since this is a true statement, that makes this a true statement as well. You could absolutely have to do that. Question?
Yeah, so the first formula, like the non-integral,
Yeah.
that's like, it accounts for like the force is at like an angle.
Right. Yeah.
That's like the integral formula. If, like,
It does because of the dot product. So when I took the integral of it, if the cosine of the angle was something else, I would have a cosine that shows up in there. Because yes, the dot product is maintained even when I put it in the integral form. So yes, it would show up if that were to happen. Absolutely. All right. Power. Power is the rate at which work is done. It's a rate. Rate. Rate goes with what? An integral or a derivative? A derivative. So power must be the derivative of something. What do we think it is? It's the derivative of work over time. So this is really important. Very important. That's why I put it up on the board. Very important to read the whole AP style question. They're going to say, and I have work and time, and I want to find power. Okay, cool. I'm taking the derivative of work with respect to time. Fine. Or they're going to say, I have work and distance, and I want force. Fine. I take the derivative with respect to x. But it's very important that you keep these two things separate because they're both work, but we're deriving them, taking the derivative of them with different things. All right? Now, that works if power for some reason is variable. So if I give you an equation for power, it is the derivative, or if I give you an equation for work, I could take the derivative to find power. So if I said a variable work of 2x squared is done for 3 seconds, what is the average power? I would just take the derivative of 2x squared and then plug in 3 seconds, right? Well, 0 and 3 seconds and then take an average, but that's how I would get power if they gave me a variable one, which they can do, absolutely. Let's say they don't though. What's the old-fashioned equation for power? Well, that's the one we use a lot, but that's not the original. What's the actual work over time? Because it's a rate of work done over a certain amount of time. That's the actual, so this is what I would use if the work is variable over time. If it happens to be, I might have to use that. But this is the equation I'm probably going to use. Except for, most of the time, right, we say this. Power is equal to work, which is force, times distance over time. So power is equal to force times velocity. I made that a W. Force times velocity. So either of these two. Honestly, this one gets used way, way more. Way, way more. Way, way. All right. Last thing, work energy theorem. Work turns into which type of energy? Work energy theorem turns into a change in kinetic energy. The reason I say that is because an object by itself can't have any other type of energy. So yes, something might do work to my system and it works out to be turned into potential at some point. That's fine. Gravitational potential probably. But originally it has to turn into kinetic because that book by itself can only have what type of energy? Kinetic. So if 2, 3, 5, 100 forces do work to this book, unless I include something else in its system, the only thing that can turn into is kinetic energy. So that's why the work energy theorem is work equals a change in kinetic energy. It might be in the situation that change in kinetic energy then turns into gravitational potential. So if we go back to me lifting the book, if I think about it, right, me and gravity are doing work to the book if it's just the book. That means we're doing equal amounts of work as it's at constant velocity, and we've done equal amounts of work when it gets to the top with the same amount of kinetic energy it ended with. If I say this is a book Earth system, then who's the only thing doing work to it? Me. I turn that into kinetic energy, which is being turned into gravitational potential as it goes up. So then it ends with a change in gravitational potential from the work that I did. But just make sure you remember that really work has to turn into kinetic energy and then into whatever it wants. Okay, let's do a lab. With very